At the end of the topic, you will be able to recall definition of a set, recall types of sets, solve problems in sets. In everyday life, we often talk about a collection of objects. Let's see some examples. Look at the first picture. This picture is the collection of flowers in a plant. Look at the second picture. This is a photograph of cricketers in the Indian cricket team. Look at the third picture. This is a collection of tasty food. The first two pictures are well-defined collection, but the third picture is not well-defined collection since this definition of tasty changes from person to person. We use the word set for a special type of collection. Only those collections that are well-defined are called sets. Thus, a set is a collection of well-defined objects. An object is an element of a set if that object is a member of the set. Example, let A be the set of the numbers 1, 2, 3, 4, 5. This means that 1, 2, 3, 4 and 5 are the elements of set A. But 6 is not an element of set A. We will see some important notations now. Capital letters are used to denote sets. Small letters are used to denote the element of a set. The names of the elements of a set are listed separated by commas and enclosed within braces. The symbol belongs to is used to denote is an element. For example, x belongs to x is read as x is an element of x. If y is not an element of x, then it is written as x does not belong to x. Sub means part of something. Let A and B be two sets. If every element of the set B is an example of set A, then we say that B is a subset of set A. It is denoted as B is contained in A. If B is not a subset of A, then we denote it as B not contained in A. For example, let set A contain 1, 2, 3, 4, 5, 6, 7 and set B contain 2, 4, 6. In this example, every element of A is an element of B. Therefore, B is a subset of A. Otherwise, we can say that B is contained in A. Look at the next example. Let set C contain 1, 3, 5, 7 and set D contain 1, 2, 3, 4 and 5. The element 7 belongs to set C but does not belong to set D. Therefore, C is not a subset of D. We can say this C is not completely contained in D. Let A be a finite set. The number of elements in set A is called the cardinal number of the set. We denote it as n of A. For example, look at sets A and B on the screen. The number of element in the set A is 5, so n of A is 5. The number of elements in the set B is 8, so n of B is 8. Types of sets. Click on each button to view the definition of each type of set. Singleton set. A set containing exactly one element is called a singleton set. For example, let D is the set of all x such that x is a natural number which lies between 4 and 6. There is only one number lies between 4 and 6, that is 5. Therefore, D is a singleton set. See the next example. C is equals to set of all x such that x minus 4 is equal to 0. That means C is the set of all solutions of the equation x minus 4 equal to 0. The only solution of the equation is x is equal to 4. Null set or empty set. A set which has no elements is called a null set or an empty set. For example, A is equal to the set of all real numbers whose square is a negative number. There is no real number with square as negative, therefore A is a null set. We write it as A is equals to 5 or A is equal to empty braces. Universal set. As the name universal suggests, this is a set which contains all the elements of all the sets in the particular discussion. Universal set is usually denoted by the letter capital U. For example, consider the following sets. A is equal to the set of medical colleges in Tamil Nadu, B is equal to the set of engineering colleges in Tamil Nadu, C is equal to the set of agricultural colleges in Tamil Nadu, D is equal to the set of all colleges in Tamil Nadu. Here in this example, D is the universal set for the discussion. We can represent this as Venn diagram as shown. The rectangular box represents the universal set. The other sets are represented by circles. Finite set. A finite set is a set which has limited number of elements. The number of elements in such a set can be completely counted and determined. For example, A is equal to set of all vowels in the English alphabet. B is equal to set of all students in class 10. Infinite set. A set which is not finite is called an infinite set. The number of elements in such a set cannot be determined. For example, W. The set of all whole numbers is an infinite set. S. Set of all stars in the sky on a particular day. Power set. The set of all subsets of the set A is called the power set of A. It is denoted as P of A. For example, let A be a set containing the elements of A, B, and C. Then P of A is equal to empty set singleton A, singleton B, singleton C, set AB, set BC, set CA, set ABC. Note that the number of elements in the power set is equal to 2 power number of elements in the given set. In the example, there are 3 elements A, B, and C. So the number of elements in the power set is equal to 2 power 3, that is 8 elements. Two sets A and B are said to be equal if they contain exactly the same elements. This is denoted by writing A is equal to B. Otherwise, the sets are said to be unequal and we write A not equal to B. Look at the example here. Set A is equal to set of all letters in the word listen. Set B is equal to set of all letters in the word silent. Even though both are different words, if we collect all the elements are the same in both the sets. The sets A and B contain the same elements. Therefore, set A is equal to set B. Two sets A and B are said to be equivalent sets if the number of elements in the sets are equal. That is, if n of A is equal to n of B, then the sets A and B are equivalent sets. For example, if A is equal to set of all x such that x belongs to whole number system and x is an even number that lies between 0 and 12, and B is equal to set of all x such that x belongs to whole number system and x is an odd number that lies between 0 and 12. N of A is equal to 5 and n of B is equal to 5. Since both sets have the same number of elements, sets A and B are equivalent sets. Here is an example of finite and infinite sets. Click on the solution button to view the solution. Let us see another example of element of a set. Give example for a finite and an infinite set. S is equal to 1, 3, 5, 7, 9. A is equals to 1001, 1002, 1003, etc. 3000. T is equals to letters in the English alphabet. Click on the solution button to view the solutions. In this topic, you have learnt that a well-defined collection of objects is called a set. The objects in a set are called its elements or members. A set with countable number of elements is called a finite set, and the cardinality of a finite set is denoted by n of A. A set with unaccountable number of elements is called an infinite set, and the cardinality of an infinite set is denoted by infinity. If every element of set B is an element of the set A, then we say that B is a subset of set A. Two sets A and B are equal if they contain exactly same elements. At the end of the topic, you will be able to define operations such as union of two sets, intersection of sets, set difference, symmetric difference, complement, disjoint sets. Define properties of sets under associative property, commutative property, distributive property. We shall learn about the following operations on sets union, intersection, set difference, symmetric difference, complement and disjoint sets. Let us learn about union of sets now. Let A and B be two sets. The set of all elements which are in A or in B is called union of the sets A and B. It is denoted by A union B. Example, consider two sets A and B. Set A contains 1, 2, 3, 4, 5 and set B contains 2, 4, 6. A union B equal to 1, 2, 3, 4, 5 and 6. Therefore, A union B is equal to the set of all x such that x belongs to the set A or to the set B. This can be represented by using the Venn diagram as shown. In the given Venn diagram, the green colored portion represents only A and the blue colored portion represents only B, and the grey colored portion represents the common part of set A and B. A union B contains the elements in all the three colors together. Now let us see the definition of intersection of two sets. Let A and B be two sets. The set of all elements which are both in A and B is called intersection of the sets A and B. It is denoted by A intersection B. Example, consider two sets A and B. Set A contains 1, 2, 3, 4, 5 and set B contains 2, 4 and 6. Then A intersection B contains 2 and 4. Thus, A intersection B contains X such that X belongs to the set A and to the set B. This can be represented using the Venn diagram as shown. In the Venn diagram, the center part represents the common part of the sets A and B, that is A intersection B. Let's now define the difference of two sets. Let A and B be two sets. The set of all elements of A which do not belong to B is called set A, difference set B, and it is denoted by A difference B. Look at this Venn diagram. Now let us remove the portion of B which is in the set A. The orange color portion represents A difference B and the green color represents B difference A. Now let us see an example. Let the set A contain 3, 5 and 7 and set B contain 1, 2 and 7. Then A difference B is equal to 3, 5. This can be represented by a Venn diagram as shown. Thus, A difference B contains X such that X belongs to A but X does not belong to B. Symmetric difference. The symmetric difference of two sets is union of their difference, that is, except their intersection. It is denoted by the symbol delta, which is read as a symmetric difference. For example, if A is equal to 1, 2, 3 and B is equal to 3, 4, then find A symmetric difference B. Solution. Applying in the formula, A symmetric difference B is equal to A difference B union B difference A. Here, A difference B equal to 1, 2, B difference A equal to 4. A symmetric difference B is equal to 1, 2, 4. Look at the Venn diagram which shows that A symmetric difference B is the set of all elements in A union B except their intersection. Complement of a set. Complement of A is the set of all elements in a universal set U which are not in A. The complement of a set is denoted by A dash. A complement is equal to the set of all X such that X belongs to a universal set and X does not belong to A. Consider an example. Let U is equal to 1, 2, 3, 4, 5, 6 and A is equal to 1, 3, 5. Find A. Therefore, A is the set of elements present in U except in A. Look at the Venn diagram. It represents the set A. This Venn diagram represents A complement. Note, the complement of the universal set is an empty set. The complement of an empty set is a universal set. Disjoint sets. Two sets are said to be disjoint if they have no element in common. In other words, disjoint sets are sets whose intersection is the empty set. Let us see an example. Let A contain 1, 2, 3 and B contain 4, 5, 6. Look at the Venn diagram. There are no common elements between sets A and B. Hence, the sets A and B are called disjoint sets. Have a look at some important results. Let U be a universal set and A and B be the subsets of U. Then the following are true. Click on the proof button to view the Venn diagram for explanation. We will now look at the properties of set operations such as commutative property, associative property, and distributive property. Click on the respective buttons to view the proof using Venn diagrams. In this topic, you have learnt the set of all elements which are combined together without repetition is called union of two sets. The set of all elements which are common to the sets is called intersection of two sets. The difference of two sets A and B is the set of elements that are in A but not in B. The complement of the set A is the set of all elements in the universal set U but not in A and is denoted by A. Two sets which have no common elements are called disjoint sets. Properties of union and intersection. Set union and intersection are commutative. Set union and intersection are associative. Intersection and union are distributive. De Morgan's laws for set difference. For any three sets A, B and C, A difference B union C is equal to A difference B, intersection A difference C. A difference B intersection C is equal to A difference B union A difference C. Let us understand the proof of laws of set difference using Venn diagram. The first law. For any three sets A, B and C, A difference B union C is equal to A difference B, intersection A difference C. Click on the proof button to view the proof. Here is the proof for second law of difference. For any three sets A, B and C, A difference B intersection C is equal to A difference B, union A difference C. Click on the proof button to view the proof. De Morgan's law for complementation. For any two sets A and B in the universal set U, A union B the whole complement is equal to A complement intersection B complement. A intersection B the whole complement is equal to A complement union B complement. Here is the proof for the first law for complementation. For any two sets A and B in the universal set U, A union B the whole complement is equal to A complement intersection B complement. Click on the proof button to view the proof. Proof laws for complementation. For any two sets A and B in the universal set U, A intersection B the whole complement is equal to A complement union B complement. Click on the proof button to view the proof.
A union B the whole dash is equal to A dash intersection B dash. A intersection B the whole dash is equal to A dash union B dash. Let us solve an example using De Morgan's laws. Given U is equal to 1, 2, 3 and so on 15. A equal to 2, 3, 7, 8, 11. B equal to 1, 3, 8, 11, 13, 15. Verify De Morgan's laws. Click on the solution button to view the solution.
In this topic, you have learnt De Morgan's laws for set difference. For any three sets A, B and C, A difference B union C is equal to A difference B intersection A difference C. A difference B intersection C is equal to A difference B union A difference C. De Morgan's laws for complementation. For any two sets A and B in the universal set U, A union B the whole complement is equal to A complement intersection B complement. A intersection B the whole complement is equal to A complement union B complement.